Welcome to the video. In this video, we're going to discuss about magnetic field. There are three chapters in the magnetic field. In this video, we're going to look at chapter 1, which is magnetic force. Under magnetic force, we will be looking at the first topic, force acting on a current conducting wire placed in a magnetic field. If we place a current conducting wire between a horseshoe magnet, current conducting wire will be thrown away. What is the reason for this? The current conducting wire will create a magnetic field around the wire, and the magnetic field of the current conducting wire and the magnetic field of the horseshoe magnet will interact, and the resultant force, as due to the resultant force, the conducting wire will be thrown away. The force which through the conducting wire is called as magnetic flux density. This force is due to magnetic flux density. This is the F. Now let's derive an expression for magnetic flux density. These are magnetic field lines. Magnetic field. These are magnetic field, and this is the current carrying conductor. Current carrying conductor. Theta is the angle between the field lines and the wire. This is the place where the magnetic field we're going to measure the force acting on this place. Delta L. We give a symbol for magnetic flux intensity. We give a symbol for magnetic flux density. We give it as B, capital B. Now let's derive a formula for magnetic flux density. The force is directly proportional to the current carried in the conductor, and the force is directly proportional to the length L it acts on the conductor, the field acting on the conductor, and the force is directly proportional to the theta angle between the magnetic field and the current conducting wire, and F is directly proportional to the sine theta. Okay, F is directly proportional to I delta L and sine theta. F equal B I delta L sine theta. In this equation, B is magnetic flux density. If the theta is 90 degrees, F equal B I delta L. We can mention this as, write it as F equal B I L. This is the formula for the force by the magnetic field. The unit of B. Okay, B equal F divided by I over L. And what is F? Force. Force we use Newton, I amperes, and L meters. And the unit for B is N Newton per ampere per meter. This is the unit, or we can call it as Tesla, or T, Tesla. If the current carrying wire is parallel to the magnetic field, the theta will be 0, therefore force will be 0. If theta will be 0, therefore BIL sine theta L and F equal 0. If this becomes 0, all equations become 0. Now we are going to look at the magnetic flux models. Flux models. The magnetic field travels from north to south. Always magnetic fields travel from north to south. Magnetic fields travels from north to south. North to south. There are about 5 magnetic models. Number 1, horseshoe magnet, and number 2, bar magnet, number 3, current carrying magnetic field around the current carrying conductor, number 4, magnetic field around circular coil, number 5, magnetic field around the solenoid. Okay, this is a horseshoe magnet, and this is a north pole, and this is a south pole. The magnetic field always travel from north pole to south pole. So the magnetic field was like this, and like this, like this. It travels like this, and from the magnetic field travels from the north pole. So these should be like this, and it's okay. And always the magnetic field comes towards the south pole. Therefore, these arrows are like this. This is the magnetic flux model number 1, and the next one is bar magnet. Okay, this is a bar magnet, and this is north pole, and this is south pole. And magnetic fields travel from, these are magnetic field lines, and they travels from north pole to south pole. North pole to south pole. And okay, and the magnetic field received by the south pole, yeah, towards the south pole. It comes towards the south pole. Next, our third one is current conducting wire. Magnetic field in a current conducting wire. Current conducting wire. If this is a current conducting wire at the center, which is coming out towards the paper, perpendicular to the paper, perpendicular to the screen. Okay, this is a wire. If we place our hand like this is our hand. Thumb should be pointing the current moving direction. We bend the finger like this, and if we bend our hands like this, and this is the direction of the magnetic field. If the current travels like this and the magnetic field is like this. Thumb points the current moving direction, and other fingers point the magnetic field direction. Okay, this is the wire, and wire is in perpendicular to us, and if we place our right hand like this, and if we bend our fingers like this, if we bend our fingers like this, if we place our fingers like this, the thumb will point the current moving direction. Other 4 fingers will show the magnetic field line's direction. So the magnetic field line travels in anti-clockwise direction. Therefore, we can mark the arrow, mark these as like this, anti-clockwise direction. Symbol we use to indicate that the current is traveling towards or out of the paper or out of the screen. We use this symbol, and in we use this as X symbol into the paper or into the screen. Just remember, I'll tell an easy simple way to remember this. Just imagine an arrow. If you're looking at an arrow is like this, right? Arrow is like this. It when it's coming towards you, and you will see in front view, you will see something like this. And so it is coming out of the paper towards you, out of the paper. And when it's going away from you into the paper, what is the arrow backwards? You see a cross mark here, like this only you will see. Therefore, remember this. This is in and this is out. There are two rules to find the direction of the current and direction of the magnetic field. First one is right hand grip rule and Maxwell's right hand corkscrew rule. Maxwell's right hand corkscrew rule. This is a corkscrew and it will be like this. And if we rotate in clockwise direction, it will move in. If the corkscrew is like this, and if we screw the corkscrew in anti-clockwise direction, it moves outwards. We use these to find the magnetic field direction of a current carrying conductor. We can use either right hand grip rule or Maxwell's right hand corkscrew rule. Next one is magnetic field around. Number 4 is magnetic field around a circular coil. Magnetic field around a circular coil. The red color part is the coil and the yellow color parts are the magnetic flux. And if the current is traveling downwards in this direction, if we look at this from this side of the coil, it is rotating anti-clockwise. If it travels anti-clockwise, what should be the direction of the magnetic flux? The magnetic flux should be coming outwards. We can use right hand grip rule here. Okay, I'll go and show the right hand grip rule. This is our finger. We have bent our fingers. Right hand rule. If we place this is a loop and this is the current. If we place the fingers in the current placing direction, this is the current moving direction, and therefore the magnetic field direction is this. Magnetic field lines direction, magnetic field lines. So the direction is like this. Direction should be the fifth. The last one is magnetic field around a solenoid. This is a solenoid and these are the magnetic field lines. And if the current is traveling in this direction and coming out from this direction, I, and this is also I, how can we find the direction of the magnetic field in a solenoid? I'll draw a solenoid here. Solenoid. And how can we find the direction of the magnetic field? This is the direction of the current and this is the direction of the thumb will point the magnetic field direction. And these are the direction of magnetic field. And which side is the north pole? Magnetic field starts from north pole and ends at south pole. Here ending at south pole and starting at north pole. Now let's discuss about Fleming's left hand rule. By using the Fleming's left hand rule, we can find the direction of motion, or I mean the force, field and the current. The thumb indicates the force. Thumb, force, and this is field, forefinger field, and the middle finger is current. This is F and this is B and I. Simply we can remember as FBI. This is X, Y, and this is Z. And here 90 degrees, and this is also 90 degrees, and this is also 90 degrees. F, B, I, they are perpendicular to each other. Now let's discuss about force on electric charge moving in a magnetic field. If the electric charge is at rest in a magnetic field, there will be no force acting on the electric charge. That the equation F equal BIL sine theta. This is the force due to magnetic field. And also we know that I equal Q over T, and V equal velocity equal distance divided by time. We will take that as L and divided by time. If we substitute these, and L equal V into F equal B Q over T into V T sine theta, and this T and this T cancel off. B equal B V Q BVQ sine theta equal F. And if the angle is 90 degrees, F equal BVQ. This V is velocity of charged particle. This V is velocity of charged particle. If the charge is moving parallel to the magnetic field, the force will be zero. Now we'll look at the next topic. Next topic is Hall effect. So current carrying conductor is based on the magnetic field. This is a conductor and this is based on a magnetic field. And the magnetic field is going into the plane. If the current traveling left side and the magnetic field into the plane, and the force will act on the conductor is downwards. Now let's consider a conductor. This is a conductor, and inside the conductor there will be electrons, and this is placed in a magnetic field. The electron travels in opposite direction to the current. Velocity of the electrons are this side V and V. What is the direction of the current? The current travels in this direction, I direction, this direction. And if we apply Fleming's left hand rule, the force on the electron will be downwards. F. There will be forces downwards on the electron. Due to the force acting on the conductor, these electron will be pushed downwards. The force acting on the conductor due to the magnetic field, the electrons will be come to bottom part. This electron will move downwards. They will move downwards, and it will create a potential difference. Upper part of the conductor will be positively charged and lower part will be negatively charged. Therefore, it will create a potential difference. These are positively charged. Upper part is positively charged and lower part is negatively charged. This creates a potential difference. This creates electric field lines. The potential difference between the X surface and Y surface we call as Hall voltage. Hall voltage. In electron traveling in a conductor under magnetic field, vertically upward force, electric field force will be there. Vertically downwards, magnetic field force will be there. The electron to travel without deviation, the vertically upward force should be equal to vertically downward force. The vertical upward force, electric force, should be equal to magnetic field force. Electric field force should be equal to magnetic field force. If they are equal, the electron will travel in straight line without deviation. This is a conductor placed in a magnetic field. Let's use this and deduce a expression for Hall voltage. Let's take the D as the height of the conducting block and the T as the thickness, and the intensity is formed due to potential difference is created. Intensity of the electric field formed due to potential difference is created. Let's write an equation. E equal VH over D. The electric field intensity is created due to potential difference created, and the electric field intensity is equal to whole voltage divided by the distance separated D, and the top part will be positively charged, and the negative part will be negatively charged. Sorry, the bottom part will be negatively charged. Here, this is the height. This is the height D and the thickness T, and this is B is the magnetic field intensity, which is perpendicular parallel to the lower surface, and this is electron E moving with the velocity U. The electron has a force of F. F is magnet force due to magnetic field downwards, vertically downwards. The force acting vertically upwards is Fe equal VH divided by D into E, charge of an electron, and the force acting downwards F equal FB equal BVE. This E is charge of an electron. Instead of Q, we are using E here. The deviation of the electron stops when these forces balance the downward forces, balance the upward forces. Downward force balance the upward force. Downward force is due to magnetic field and upward force is due to electric field intensity. Electric field force should be equal to magnetic field force. Okay, let's look at this equation. VH divided by D, and here BVE into E, charge of an electron, and this E and this E cancel off, and the final equation will be BV into D. BV into D. I'll clarify this equation using this diagram. FE, this is FB, magnetic field, and this is the velocity, and this is I, current traveling direction, and this is magnetic field. Okay, this is x coordinate, and this is y coordinate, and this is z coordinate. In electricity, we have learned that I equal area into number of electrons into electron charge into V. We call it as ane V, ane wade, and this is the area, cross-sectional area of the block, number of charge carriers, this charge of a electron or charge carrier, this is velocity. We substitute velocity, V equal I divided by A N E, and we're going to substitute this V to VH equal BVD. Let's substitute those equations, and this is equation number 1, and this is equation 2. 1 should be equal to equation 2, and this is the reaction number, sorry, formula 3, and this is the formula 4. Substituting 4 to 3, VH equal BVD. If we substitute it, VH should be equal to P into I divided by ANE into D, and this area is equal to D into T. This is the area, D into T, D into T. and VH equal B into I divide by D into T NE into D, and this D and this D will be cancelled off, and the final VH equal BI divided by NET. We can derive another equation for velocity. Let's look at that. FE equal FB. We know E into Q equal electric field force into BVQ, and this Q will be cancelled off, and we can subject V equal E over B, electric field intensity divided by magnetic field intensity, and but E is equal to VH over T. If we substitute that, this is number 5 and this is number 6. Substituting number 6 in number 5. V equal E over B, and V equal VH over T divided into B, and the velocity is VH dB. This is the equation. And that's all for chapter 1. Thanks for watching.